G'day Clansman enthusiasts, it's Alex here, Victor Kilo 2, Papa Radio Charlie, over here in Australia. Recently, a friend in the UK sent me a power supply, this particular one here, and the power supply was a dud. It wasn't working, so he kindly donated it to me to keep, but to fix up and keep. But he mentioned to me that he would like me to do a video on basically repairs and a little bit of maintenance on these particular power supplies, so that people that view this particular video of mine will have a better chance to do repairs and maintain their Clansman 320 radios. So I agreed, and since then I've repaired this particular power supply, so it's fully operational now. And what I'm going to do is I'm going to go through the power supply in a lot of detail and try and explain, number one, how it works, but number two, some repair tips and things you should really be looking out for when you're maintaining the power supply in your 320. Now, we all know, us 320 owners out there, that this particular power supply is a very complicated little beast, and it's in a small package, and it's the Achilles heel of the Clansman 320 radios. Pretty well, if you have a failure on the radio, 95% of the time it's going to be in the power supply. So it's really good to understand how it works and how to repair it and all the little bits and pieces associated with it. And look, in this particular video, I'm going to incorporate a lot of knowledge that other people have found and contributed, online in forums, etc., to add to what I've got as far as my information. Look, by no means I'm a full big expert on these power supplies, but I've got a pretty good idea of how they work and things to look out for when you're repairing them. So I'm going to put it all into this particular video, and it's quite a long one, and I'm going to work on this particular power supply here, and I'm going to use the drawings here that kindly have been formally analysed by a chap in the UK quite a few years ago. There he is there, Martin G8 JNJ, I think it is. He's put together some very, very good information on these particular power supplies, as far as all the associated voltages that should be expected at different parts of the circuitry. So what I'm going to actually do in this particular video is I'm going to split the power supply into 4 sections, and we're going to look at each section individually. The first section that we're going to look at is the 12-volt section of the radio here. It's on the board closest to the base of the power supply, just adjacent to the socket that provides the inputs and outputs from the radio. Purpose of the 12-volt section is twofold. The first is it provides a nice regulated 12 volts to run out of there, to run the reference oscillator in the radio. Secondly, it provides power to run the rest of the power supply out of here. Okay, so it does 2 things. Without the 12-volt section, nothing works. Okay, the next section on the same board, this is the bottom board on the power supply, is the 3-volt section, and this particular regulator here provides power to run the synthesizer and the tuning section of the radio. Let's look at the top board. Okay, 12 volts comes up onto the top board by a little jumper lead up here. And first of all, it supplies the 6-volt section of the radio. The 6-volt section of the radio mainly provides power around the motherboard area, but it does another thing too. It also supplies an oscillating voltage, an oscillating current, just at the base of that transistor, and that pulsates a current through that transformer, which is a 10-to-1 up transformer, high voltage on the other side, rectified, regulated here in the last section of the radio, which is the high voltage 110 volt section, and which provides the high voltage required for the voltage control tuning on the radio. So just to summarize again, we need the 12 volt section for any of the sections of the power supply to work. And yeah, each particular section can fail, but some sections will cause other failures. For instance, if you've got no 110, you may have no 6 for sure, and you may not have 12. If you've got no 6, it may be a problem here, but it may be a problem on the 12. So it's always advisable to check the 12 volt supply first, because the 12 supplies power for the 6, and if you've got 6 and you've got no 110, then you've got a problem in the 110, if you know where I'm coming from. All depends on the 12 volt section. So that's the very first section that we're going to look at today, the 12 volt section of the power supply. Okay, the first section of the power supply that we're going to look at is the 12 volt section. This is the main section of the power supply. Power supply doesn't work unless you've got 12 volts going. So very important, this particular section. 24 volt comes in through the socket, through the diode, through this filtering inductor, and that inductor works in conjunction with this 22 microfarad electrolytic capacitor here, providing a nice smooth voltage to run our integrated circuit ML1. ML1 is the heart of this particular 12 volt section of the power supply. It provides a square wave, pulsing square wave at pin 4. The pulsing square wave at pin 4 is controlled by the potentiometer here on pin 1. As we regulate this particular potentiometer, it changes the pulse width coming out of pin 4. The pulse coming out of pin 4 pulses this transistor and the main power transistor, because they operate in a Darlington pair. Okay, so coming out of the main power transistor, we've got a series of very high frequency pulses, and those pulses are then smoothed up into a pretty nice DC supply by these capacitors over here, a 22 microfarad and a 68 microfarad capacitor. These capacitors, in conjunction with these inductors, do the smoothing, so we end up with a nice smooth DC. This particular DC supply here goes off to the reference oscillator, the 12 volt that drives the reference oscillator, and this 12 volts here goes off to supply the other board, which generates the 6 volts and the 110 volts, and it also goes down here to the 3 volt section that we'll be looking at next. So as we control the potentiometer, that controls the pulses control the average voltage over here. Feedback loop back through this little resistor here, back through the potentiometer, so we've got a constant feedback loop. By varying the little potentiometer here on the pulse widths, we can tune up our 12 volts to the correct voltage. And I've found that the prescribed correct voltage that I like on my power supplies is about 12.6 volts. So let's now have a look at the components that I think are very important in this little part of the power supply. Okay, when it comes to repairing this part of the power supply, these particular transistors, they're still available. There's a BCY70, and I think the other one's a 2N3720. Both of these transistors are available on eBay UK. Okay, and I just want to talk about the main power transistor. The main power transistor is an absolute little beast. It's a military grade. It's a very high power dissipating transistor and a very high current transistor. I haven't really been able to find a replacement for it. So while the original is still available, I wouldn't worry about it. I would simply use the original transistor if it fails. Normal testing on these transistors, just using your meter with a base emitter, base collector, conducting sort of tests on both the transistors, usually shows if there's any failure. And the one that usually fails the most is this little fellow here, okay? The little it's under high stress, that particular transistor. So other faults on the power supply can reflect back here and take out this particular little transistor, okay? So be aware of that. The other things the other components of note are this little capacitor down here. These little electrolytics on the power supply, they've been there since about 1980, and yeah, they dry out. They lose their value. So when I maintain these power supplies, whether I'm doing repairs or just the maintenance on them, this particular power capacitor here I normally change, and these two over here, and these provide the nice smoothing filtering for the reference oscillator and also the rest of the power supply. So yeah, if I ever have to come here to replace, let's say, this transistor, I'll go along and do these diodes here as well. But look, let's just have a look at how this particular thing works. And Martin's provided all of these lovely voltage references, the DC values, which are up here, average values, etc., to go around the circuit and try and pinpoint a failure. But bear in mind, no pulses out of here, no work. So I find it very, very important when working on these power supplies to have my crow on hand. So let's just have a look at the pulses that we're going to get coming out of 4. We'll look at the pulses that we're getting into the main regulating transistor, and lastly we'll have a look at the pulses coming out of the collector of that little power transistor when it goes over here before it gets smoothed and filtered. So yeah, if you're working on a particular power supply, having these little wave shapes to have a look at, to refer back to, very, very important. So let's get the crow going, and we'll do a couple of quick testing. First of all here, secondly here, and thirdly here, and have a look at what we should be expecting on this power supply. Okay, in order to do the testing on this particular power supply and show you the wave shapes, etc., I'm using my power supply test rig. What I've done here, I've got myself a spare plug, and I use it to plug into the power supplies under test. I've got load conditions here for the 3 volts, 6 volts, 12 volts and 110 volts. I provide power to my little test rig via a battery. Simple as that, with a couple of alligator clips. Okay, so first of all I'll power up the power supply, and then we'll go and have a look at the test points here. I think that's the first transistor that comes out of the little integrated circuit, and then just under there is the main power regulator transistor. We'll have a look at the wave shapes from those test points there. So in order to isolate the correct test points to make these tests, I find it very, very easy to use a bit of information that was sent to me by a very good friend of mine in Canada, Paul, Victor Echo 1 Papa Victor Hotel. Paul's created this very, very interesting and valuable little diagram here that shows the layout of all the components on the boards. This little board here is the 5A board, which is the bottom board, and this one here, the 5B board, which is the top board. So there you go. Let's find the test points and show some wave shapes. Okay, I'm now monitoring the base of the first little transistor in the Darlington pair. This is coming out of the number 4 pin. I've got the crow set on 0.2 of a volt per division, so 0.2, 0.4, 0.6, 0.8 of a volt, and it's running at about 43.6 kilohertz. Nice little square wave coming out and driving that first little transistor. So next, let's have a look at the base on the main power transistor. Okay, there's the base on the main power transistor. It's following the pulses from the leading transistor of the Darlington pair, and this time it's 0.2, 0.4 and a bit. Yeah, about 0.5 peak to peak. Same frequency, of course. Yep, and that's driving the main regulating transistor. So let's have a look at the collector on the transistor, which is the 12 volt side of the main transistor. Okay, and that's going to be much higher, so I'm going to have to change my scale here, and I've got that down now to 5 volts per division. So of course same frequency, but you see that coming out of the main regulating transistor is in fact a pulse train, and there it is there, 5 volts per division, so 5, 10, 15 and a bit. and that's coming out of the the main transistor. And of course, these pulses then charge up the two loading capacitors, and they provide the smooth voltage for the remaining parts of the regulator, and of course the main reference oscillator for the radio. So there you go. The main Darlington pair in the 12 volt section of the radio in fact works on pulses. Okay, the next section of the power supply that we're going to look at is the 3 volt section. This is the section that provides the 3 volts for the synthesizer and the frequency selection on the radio. Now you'll recall our 12 volts was produced and put a nice little charge into this capacitor here, this 68 microfarad capacitor, and this particular capacitor smoothed the 12 volts up for the rest of the radio. So, yep, over here into the 3 volt section. It also goes up to the next board, which is the 6 volt section we'll look at next. Okay, so our 12 volts through a nice little smoothing inductor in conjunction with a smoothing capacitor again. Very important that this little capacitor be working properly, and to give that nice smooth 12 volt supply for the ML2. Now ML2 happens also to be a little switch mode power supply controller. So yeah, here it is, very, very similar to the 12 volt ML1, and what it provides again is a train of pulses coming out of the number 4 socket, and that little train of pulses pulses the leading transistor in the Darlington pair, which controls the main power transistor for the Darlington pair and produces the 3 volts. This particular transistor is also a pretty rugged one and needs to dissipate a bit of heat because of the power dissipation, which is 12 volts down to 3 volts. Okay, so over here we end up with a train of pulses again. That's going to be our 3 volts eventually, and that train of pulses comes up here and charges up this 330 microfarad capacitor, and also gets filtered again and finally charges up this 47 microfarad capacitor, which provides the 3 volts for the synthesizer. Feedback down here again onto the potentiometer, and as we vary the potentiometer, exactly the same as the 12 volt supply, we vary the pulse widths here, and we're able to adjust the output voltage. Again, these transistors here are easily checked by using the base to emitter and collector test with a normal multimeter. Okay, so let's now have a look at the main components and what I think are pretty interesting and important things when it comes to servicing this part of the power supply. Okay, when I service this part of the power supply, invariably the main transistor seems to fail. So it's a bit of a difficult one to get, BFS 97K. So I've been able to find a very, very nice little substitute for this transistor here, one that's even a little bit more rugged than the original, and it's a ZTX 550. There they are right there. ZTX 550, readily available on AliExpress. They're quite cheap, but you've got to buy a whole heap of them. But you know, $10 or something, and you buy yourself a lifetime supply of these ZTX 550 transistors. And as I say, they're a very, very nice little replacement for the main power transistor in this particular circuit. Other parts of the circuit that I find very interesting and need to be serviced as well, again, is the 22 microfarad capacitor here, which provides the nice smooth filtering for the supply for the ML2 integrated circuit. And of course, coming out here, we've got a 330 microfarad capacitor here, which is going to smooth up our 3 volt supply. And lastly, 47 microfarad capacitor here for the final output stage of the 3 volt power supply. If you can't get that one, I'd be at least changing this one for sure. Okay, so that's basically the components that I find important and and the replacing of as far as maintenance for this part of the power supply. So let's now go on and have a look at our pulses that we can expect to find here at the base of the transistor, here at the base of this transistor, and here at the collector, which is the output from the main power transistor. And I'm thinking it's going to be very, very similar to what we've seen on the 12-volt power supply. Okay, the first test point that I'm going to go on to is the base of TR4, which is the first transistor coming out of the integrated circuit. There we go, this one's running at 33 kilohertz. Okay, so let's have a look. It's on the 0.2 of a volts per scale, so 1, 2, 3, 4, 5, 6, well, about 5 and a bit, so it's about 11 volts. Yeah, coming out of there, 11 volts peak to peak at 32.9 kilohertz. Okay, next test point, we'll look at the base on transistor 3, which is the main regulating transistor for the 3-volt supply. And we may have to do a little bit of a little dance there. Okay, same frequency, of course, very well, pretty close. And this time it's running at 1, 2, 3 divisions. So there you go, 0.2, 0.6, 0.8 volts per division. That's the base of the main regulated transistor for the 3-volt supply. Lastly, we'll have a look at the collector, and the collector, of course, will be a much higher voltage, so we'll have to go around here. There we go, and there it is there. So you can see the pulses coming out of the transistor, heading for the smoothing capacitors. And looking at it here, it's about 0.2 per point. What is that? 0.2 per division, so it's 0.2, 0.4, 0.6, 0.8. No, sorry, mistake, 2 volts per division, 2, 4, 6, 8, a little over 8. But the off time is quite long to the on time, which is going to give you an average of around 3 volts. Okay, so there you go, interesting. There's the wave shapes for the 3-volt power supply. Okay, moving along to the 6-volt section of the power supply. The 6-volt section's got 2 functions. So first of all, we're going to talk about the first function, which is the production of the 6 volts, and then we'll move on to the second part. Okay, 12 volts comes up here from the 12-volt section, which is the board below. Now we're onto the top board of the power supply. The 12 volts is smoothed through a series inductor, parallel capacitor that pumps up and gives us a nice voltage, a smooth voltage to control our switch mode power supply integrated circuit. Again, similar to the previous 2 sections of the power supply, we've got pulse trains coming out of pin 4, controlling the first transistor in the Darlington pair, controlling the second transistor, which is the main power transistor, and producing a set of voltage pulses to the output. Okay, so across down here, pumps up quite a big capacitor, in this case 330 microfarad capacitor, and that gives us a nice smooth 6 volts, which is taken out to the 6-volt section of the radio around the motherboard area and places like that. Feedback's provided back through the controlling potentiometer, which gives us our controlling loop as usual. As I said before, controlling the potentiometer controls the pulse width of the pulses coming out of here, and hence the output. So round and round it goes. By adjusting this, we can adjust our nice 6-volt power supply up to the required voltage. So let's just have a look now at some of the interesting components when it comes to maintaining this little part of the circuit. Okay, when it comes to maintaining and repairing this part of the 6-volt section, my first thoughts are electrolytic capacitors. So the 22 microfarad that's used in the initial filtering for the little integrated circuit is very important, and if I was doing maintenance, I'd be looking at changing that little electrolytic. The same as the 330 microfarad electrolytic over here, which provides the smooth 6 volts for the motherboard on the radio. That's very important to slip a new one in there. As I say, these capacitors are quite old and they deteriorate over time. Okay, one of the biggest failures in this part of the circuit is, again, the main power transistor in the in the circuit. So it's a little bit of a difficult transistor. And notice there it says BF 597K. I think that's actually a misprint. According to the parts list in the manual, it's a BF 97K. Don't know where the 5 comes from, but nevertheless, pretty well impossible to get your hands on. But luckily, our replacement transistors, our ZTX550s, work extremely well in that position. So again, available from AliExpress, and slip one in there. In fact, this particular power supply that I've just repaired has got one in it because I've just put it in. That was the mode of failure in this particular power supply. So they do work very well, and they're easy to get your hands on. Okay guys, so what we're going to do now, we're going to have a look again at the pulses on the first transistor, the second transistor, and the collector, and just have a look and see exactly what goes on when we well, run the power supply. So let's have a look at the wave shapes and take it from there. Okay, we're looking at the base of the first transistor on the Darlington pair. That's coming out of pin, I think it's pin 4 again on the integrated circuit, into the first little transistor. 0.2 again scale, so it's 0.2, 0.4, 0.6, 0.8, about 0.9 peak to peak. We're running at about 38 kilohertz. So that's the wave shape you should expect coming out of the little switch mode integrated circuit. So next we'll have a look at the base on the main power transistor, and there it is there again. Same frequency, of course, so that's 0.2, 0.4, about 0.5 peak to peak pulses on the base of the main regulating transistor. Lastly, we'll have a look at the collector, and this is what we should expect to see on the collector, coming back down here to I think it's 2 volts per division. So 2, 4, 6, 8 and a bit, so let's say 9 volts peak to peak coming out of the regulator. And of course the off times and the on times would average out around about 6 volts. So of course about the same frequency, yeah, about 38 kilohertz. Okay, so they're the 3 wave shapes you should expect when you're monitoring the 6 volt regulator. Okay, let's have a look at the second section of the 6 volt power supply. And this is to do with the creation of the high voltage, okay, for the next section, which is the 110 volt section. So you'll recall we've got about 38 and in some cases up to 40 kilohertz being produced as a pulse train in this part of the 6 volt regulator. Well, what it uses is that particular 38 kilohertz pulse train to pulse the base of this particular transistor here, TR3, and as the base of this particular transistor pulses at the same frequency as the 6 volt power supply, it switches this little transistor on and off. Now you notice here that goes back to the 12 volt section, so we've got 12 volts being applied up here, and it's being switched on and off through this particular transistor here to ground, and it's running through the primary of this little transformer T2. This particular transformer is a step-up transformer, a 10-to-1 step-up transformer. So in order to give our transformation, we've got movement, which is the switching of the current through the transformer. On the other side of the transformer, high voltage is produced, and I will be talking about that in the next section of the power supply. But in order for the high voltage section to operate, we need this particular transistor here to switch on and off at about 38 to 40 kilohertz and produce the energy required for transformation up to higher voltage. So let's have a look at some of the parts of this particular circuit that may cause a problem. Okay, now when maintaining this little part of the circuit, often this little transistor BC107 fails. and it can fail because of problems over here on the 110 volt supply that are reflected back onto the primary side of the transformer. Okay, so yeah, they can run hot and they can fail. Now look, it's an easy thing to replace the BC107, but I've been advised by those that do a little bit more work to these power supplies than I do, that that you can replace this transistor with one with a higher gain, which is a BC109 transistor. And the BC109 having the higher gain can produce slightly a higher voltage over on this side of the transformer, which can be advantageous to the high voltage side. But whether you replace this with a 107 or a 109, completely up to you. But they tell me that when you pick a replacement BC107, you should be looking for one that's got a good gain. So perhaps do a gain test on half a dozen and pick the best one, slip him in there. There you go. All right, another point of failure is this particular diode here, D1. So whenever you've got problems with this part of the circuit, you should be looking at number one, the transistor, and a little diode here as well. Okay, guys? So there you go. Let's have a look at the wave shapes to expect around this particular transistor. Okay, we're looking at the base on TR3. We've got the crow on 0.5 of a volt, so it's about 1.5 volts square wave on the base of the little 107, BC107. Okay, let's have a look at the collector. This is the one that goes to the transformer. So there we got it on the 2 volts per division. No, the 5 volts per division. So 5, 10, it's about 15, 17 volts on the primary side of the step-up transformer. And again, you'll see that it's about 38 kilohertz pulsing into the primary of the step-up transformer. And that's the function of the little BC107 oscillating transistor for the transformer. Okay, which finally brings us to the final part of the power supply, the 110 volt part. Now look, this particular part of the power supply seems to give people the most heartache when it comes to faults and failures in the power supply. So let's have a really good look at this bit. Okay, in order to get any sort of voltage on this part of the circuit, we've got to have TR3 oscillating there, giving us a transformer action 10-to-1 step up here. Okay, so over here, expect to find a voltage that would be 10 times the primary volt. So it's pretty high, and it's a nice pulsing high voltage. That's rectified through this full diode bridge, and there's a test point on the board, and I think the test point's around about here, where we test for the 121 volts. Very, very important to have that 121 volts at the test point, because that's the voltage on the unregulated side of our main regulation transistor. Okay, so when we look at how this particular thing regulates, down here we've got a very, very important voltage. It's 5.78, and everything starts here. That voltage there is a combination of this particular feedback resistor here, this particular capacitor here, but most importantly, this little ML2 integrated circuit. Now, this particular integrated circuit is not a big mystery. A lot of people think, oh, my chip's gone, my power supply is no good anymore. Not so. So what this particular thing is just simply this part of it here acts like a Zener diode, putting that voltage on here. Okay, so that's a very, very important thing to start off with, to have that correct voltage here. And this part of the circuit acts simply as a diode, and this gives temperature compensation for a change in ambient temperature on the power supply to keep the high voltage stable. So yeah, very, very simple little integrated circuit there. It's not a mystery after all. Okay, so we've got our reference voltage here, and between this transistor and this transistor, we've got our Darlington pair, and they operate in conjunction with these other transistors over here to give us the voltage regulator that we need to get our voltage down from the high voltage of 121 down to 110. Feedback loop through here and through R11. So by adjusting R11 up and down, it adjusts the output of our particular circuit. Now, within the circuit, there's a very important parts when it comes to maintaining a nice smooth regulation, and we're going to look at those parts next and the modes of failure on this particular board. Okay, the very first thing that comes to mind are these diodes. Now, if these diodes fail, of course, we're going to lose our high voltage, and our power supply is going to collapse. So in the case of these diodes, they're a simple test using a standard multimeter to find out if your diodes are in fact shorted or whatever. And remember when I said that faults can reflect back on this transistor? Yeah, you can have all sorts of things like shorted capacitors or shorted diodes that short out the primary side of the transformer that can reflect back and damage that particular transistor. So yeah, watch out for that. So if these diodes fail, or if you have one of them fail, I certainly suggest changing the 4 of them, and they need to be fast switching diodes. And the brand that comes to mind is Scotch. I'm having trouble here. Scotch T diodes. They are very fast acting diodes and work extremely well in that particular application there. Okay, so if we've got our diode bridge that's working, as it should, this particular capacitor, this one here, is the capacitor that everybody seems to change in their power supply, and it's a very important capacitor as well. It's down there is 36 microfarads, but we seem to put a 47 microfarad capacitor in there, which is really important. But the voltage is very important on these capacitors. No good putting 125 volt capacitors there. You need much higher voltage than that. At least 160 volt capacitor. So when it comes to maintaining these power supplies, this capacitor is a must for a change. Been in there since 1980. It's a tantalum. Take it out, replace it with a nice, good quality electrolytic with a voltage of at least 160 volts. Okay, moving along. We've got our main power transistor, and look, the other transistor here in the Darlington pair just happen to be the same transistors. And these little buggers are hard to get, again, like impossible. What is it? FRB 700s, both of them. But luckily, we've got a replacement again, and that replacement happens to be a ZTX 857, and there's one just sitting there. A ZTX 857 again, readily available from AliExpress at a very reasonable price. You've got to buy a fistful of them, but it doesn't matter. Okay, and they are absolutely fantastic replacements. I think they're a 300 volt 1 amp transistor. So if you get a failure on the main regulating transistor, which is quite common, I would suggest changing them both. Put them both to the new type, ZTX 857. Okay, all good. And that's quite evident by having a high voltage on the collector and nothing on the emitter. Is usually a dead giveaway that something's going on here, and that could be caused by down here, etc. Okay, so again, all these transistors can be tested easily by just the base collector emitter test with a standard multimeter. Okay, moving along. Right, down here, the 5.78 volts is very critical for everything to operate. And I found in the past that this C7 47 nanofarad capacitor fails quite often. So in the course of events, and I was doing maintenance on a power supply, I'd be coming in here and changing this capacitor just as a matter of course. And I'd be putting, instead of a 50 volt capacitor, I'd be putting a 100 volt capacitor in there. Okay, and yep, these are pretty readily available polystyrene capacitors in there. Okay, they're about the same size physically, fits straight in. Okay, moving right along, we're looking at this this ML2. Okay, this is a bit of a mystery. Everybody thinks my integrated circuit fails. I'm in all sorts of trouble. Yeah, get another power supply, but not so. We can actually repair this, so to speak. So this part of the integrated circuit here acts like a Zener diode and provides the voltage up here at 5.78. If that fails for any reason, it's a very, very simple method of putting in a 5.6 volt Zener in here with a diode in series, and that will get you out of trouble. You can eliminate this part of the integrated circuit by just shunting it with a Zener diode and a diode in series, and gives you the same effect, and you've got your voltage back up here and away you go. Pretty good, eh? And this part of the circuit here, if this particular part fails, it can be replaced by a standard diode. So that'll give you the standard diode. Will give you the temperature compensation as this original part of the integrated circuit used to do. And just to point out, this particular power supply that I've inherited here and just repaired happens to have a diode in that position. So there you go. Somebody's come up with the problem before and replaced it with a diode. So there you go. Okay, and lastly, this particular capacitor here, C8, is a 1.7 microfarad capacitor, and that's the final smoothing capacitor for the outgoing 110 volt supply. And again, that should be changed at the same time you change this one over here. Very, very important. And instead of a 1.7, we use a 2.2. Very high voltage again. Next, I'd like to discuss the ramp up of the 110 volt supply. When you first turn the radio on, you'll probably notice that it takes a little bit of time for the radio to lock. This is caused by the 110 volts slowly increasing in value and ramping up to the set value that you've got it set. Some believe that the capacitors in the synthesizer need to charge up, and there's two of them in there. They're about 10 microfarads each, and that's the cause of the ramp up. Others believe that this RC network here, this resistor and this capacitor, causing the voltage to ramp up at that point there and causing the regulator to ramp up overall. So what I'm going to do is I'm going to put this little, well, it's not a myth, but this question to bed. First of all, I'm going to turn the power supply on with some simulated capacitors in circuit, and these simulating the capacitors in the synthesizer, and we'll have a look at the ramp up, and then I'm going to disconnect the Q capacitors, and we're going to have a look at the ramp up without them, and see if in fact it is the capacitors causing the ramp up or not. So let's do that. Okay, I've got it connected up now with the capacitors connected. So let's have a look at the ramp up on the voltage. By the way, with the test rig here, you've got to switch the load on and off for the 6 volts to get the power supply to operate properly. Yeah, a little bit of a feature of the power supply. It needs to have the load switched for the 6 volt for the oscillation to start working on TR3 and the transformer action to start across the transformer. So let's have a look at our ramp up with capacitors. As you can see, there's the ramp up. Okay, it's getting pretty close to its peak now. Okay, so there we have the results with the capacitors. So now what I'll do is I'll disconnect the capacitors and we'll do it again and have a look at the ramp up. Okay, I've just disconnected the load capacitors and ready to start up power supply again. Let's have a look at the ramp up with no loaded capacitors. There you go. That's loading up now. Well, without the capacitors. Well, I'd have to say that the capacitors probably made very little difference to the ramp up, which only goes to show that, in fact, it's the RC circuitry in the power supply that that governs the ramp up, not the load capacitors in the synthesizer. So there you go. Okay, when it comes to setting up the final voltages for the power supply, I do it on my test rig. So I've got, as I said before, I've got the correct load resistors here, and there they are, by the way, 3, 6, 12, and 110, and I think that's 18K there. And I've got a couple of capacitors in here that simulate the capacitors in the synthesizer, which you can watch ramp up when you turn the power supply on. Okay, so let's have a look at the preferred voltages. And by the way, I set these voltages up with my power supply under load on the test rig. Okay. All right, so 12 volts, 12.6. That's my preferred voltage, 12.6 on that side of the power supply. Over here, the 3 volts, 3.03. Okay, that's required, definitely not under 3. Okay, we'll have a look at the next one. The 6 volt, around 6.05, yeah, just above 6 volts is my preferred there. But when it comes to the over here, I take a lot of advice from a chap I know, Mark, VK2WU down in Wagga. He's done a lot of work when it comes to the voltages set up on these part of the regulator. And according to Mark, it's more advantageous to have what he describes as headroom. So on the unregulated side of the power supply, it's important to have a voltage up around here, around 121. If it's got anything less than that, you should be looking back at this transistor and why it's not up here, all right? So, yep, you need that high voltage there. And on the low side, you need enough difference between the voltage here and the voltage here so that when you hit the PTT, the unregulated side, and this particular capacitor here, gives out energy, which dips the voltage a little bit on the primary side of the regulator, so that as you're hitting the PTT or tapping a key, the voltage dipping is going on this side of the regulator, and this side of the regulator stays nice and rock solid. In order to get enough headroom, you don't want these two voltages too close together. And by the way, the radio over here doesn't really require 110. The voltage over here is only really for tuning, and the radio will tune quite well at about 104, 105 volts over here, not a problem. So my recommendation over here is around about the 105, 106, rather than the 110, which maintains a greater headroom, allowing more energy over here to be transferred over here in times of load. So yeah, that's my opinion when it comes to voltages for the setup of the power supply. So there it is, guys. About as much as I know about these power supplies, and how to look at them in a different light, and how to repair them, and the typical things that go wrong. And thank you very much to the donor in the UK that donated the particular power supply here that I was able to make this video with, and with the help of others like Mark VK2WU for his information concerning the high voltage, and Paul VE1PVA helping us explain these particular positions of the components on the boards. So what I'm going to do at the final part of this video, I'm going to just put up the diagrams that I've shown, so you can freeze frame and copy and print page or whatever you may like. So here is Martin's, by the way, Martin G8JNJ. This is his work. So if you want to freeze frame there, that's the 2B board. There's the 2A board. Okay, freeze frame and copy that one. And lastly, there's Paul's diagram that he's made up of the layout of the components on the board. Very, very invaluable, that one. Saves a lot of time mucking around tracing circuits. So again, freeze frame and make a copy of that. So good luck, guys. Thank you very, very much for looking at my video. And the whole intention was to put this video up as an in-depth video on the power supply. Never seen one before, and I thought, look, I don't know everything about them, but I know a lot. So I've transferred that onto this video, and I hope it benefits people throughout the world who have got problems with their power supply and need a bit of a leg up. So good on you guys. Thanks for maintaining the Clansman 320 radios. This is Victor Kilo 2, Papa Radio Charlie Alex over here in Australia, saying 73 to all and catch you on the air.